I'm Dr. Arico, faculty in biomedical engineering at University of Hartford, and the presentations that we're here today for are the senior design presentations for biomedical engineering. It's a 2-semester class, so the students have 2 semesters to design, test and build and test and then retest and redesign their projects. And so this year we had 5 groups and 5 different projects, and everything was pretty much successful.
Hi, I'm Lydia. And I'm Alyssa. We're from University of Hartford Biomedical Engineering program, and we had a really great time working with Jim. He was really helpful, and we were able to get our prototypes of our prosthetic feet made from him. And
yeah, their manufacturing technology program was able to make these feet with their numerically controlled milling device out of this plastic Delrin. So that was a great way to make the feet much less expensive than 3D printing or something like that.
Group number 2, and this is Wista and Lydia and Tana as well.
So by the end of the fall semester last year, each group member proposed a design idea to the team, and then we rated these ideas based on a Q matrix with weighted design criteria. And the rocker foot had the highest rating. It's just a simple arc-shaped foot seen there. Because it met all the design criteria, it was durable, functional, and inexpensive, and most importantly, it's easy to manufacture. So the next step was to perform research to determine the best curvature to use. We wanted a curve that would be the most energetically advantageous and also require the least amount of work from the user to walk in. So from research, we decided on a curvature with a radius of 0.3 times the leg length.
to make our rocker foot a little bit more advanced and higher quality, we decided to add a split toe feature to it, which we were hoping would add better pronation and supination on the foot. And we also wanted to add a spring in the heel for energy absorption at heel contact. The top sketch and the foam prototype we made, these were the first proof of concepts that we had. These didn't have the correct curvature on the bottom of the 0.3 times the leg length, so we then redid our SolidWorks drawing, and that drawing is our final SolidWorks prototype.
Before spending money to make a prototype, we wanted to make sure that the curve would perform well when it's being walked on and the user would think it feels good as they walk. So we just used a test foot out of wood. We traced the curvature onto the wood and used bandsaw and a belt sander to smooth the edges, and then used contact cement to attach the foam sole to provide cushion and traction for the user.
We then performed subject testing on this foot, and we collected data to see how it would compare to normal values. So we collected on the gait rate, and we collected velocity, cadence, step length, and percent stance for the prosthetic foot. We then also collected on force plates that have 6 degrees of freedom, and we found the ground reaction forces at heel contact, mid stance, and toe off, and then the inferior moment, which is the twisting moment of the foot. We thought that the maximum value of that was important because twisting of the foot then affects the rest of your leg as well. This is a video we have of our subject walking on the rocker foot. This was before we added the foam, so we had laid out 3 different types of foam of different stiffness and to see what our subject preferred, and then we added the foam.
Before making the split toe foot out of Delrin, we wanted to make sure that it wouldn't fail under normal walking loads. So we did finite element analysis in SolidWorks software. We virtually applied loads to the part to see how it would behave. So we first applied the material properties of Delrin to the part in the software, and then applied loads by the force plates during subject testing to the heel and the toe regions of the foot to mimic walking forces. And you can see in the picture on the top left, it's the deflection. It looks like a lot, but it's only 4 millimeters, which really is insignificant. And then this is the stress in the foot after the loads were applied. It's concentrated mainly in the heel region, which justifies our need for a support there to distribute the loads. After FEA, we contacted Windham Technical High School, their manufacturing program. We sent our SolidWorks drawings to them, and they were able to make the foot out of Delrin using their numerically controlled milling device and a Mastercam CAD software. And then we were informed there that the machine wouldn't be able to do the socket for the spring like we initially intended, so instead we decided to go forward with rubber blocks in the heel region to absorb the energy. It'll behave the same way as the spring. And then we used a drill press to add threaded inserts to the top of the foot so that the pyramid adapter would be securely attached.
We then did subject testing on the split toe foot, and once we got the split toe foot, we realized it was humongous and really heavy. So we can pass this around too. So we decided to move forward with our newest and final prototype, which is in our narrow foot. It's about half the size of the split toe foot, and it doesn't have the split toe in it because we found that the Delrin doesn't really give enough to actually provide the pronation and supination that we had wanted.
We performed FEA on the narrow foot as well before manufacturing it out of Delrin. And the deflection here is a little bit larger than the split toe foot, it's 6 millimeters. And then the stress is also concentrated in the heel region, which will be compensated by the rubber stopper. And then after doing the FEA, we contacted Windham again, and they made the foot with the same techniques. We made this foot 2.25 inches wide, which is just wide enough to fit the pyramid adapter at the top.
We did subject testing again and have a video, and you can see it looks really good, this new prototype. We then compared our results from all of our subject testing trials to our subject's everyday prosthetic foot to see how the values would compare. And we performed 3 trials on each foot for each type of data collected and then averaged all the values, which are the ones you see here. So for the gait right data on the top, our narrow foot had the values that were closest to the silhouette control group for velocity, step length, and percent stance, which made us think that the subject's probably the most comfortable on the narrow foot compared to the other feet that we tested. And then for the force plate data, the ground reaction forces at heel contact, although ours were still higher for the narrow foot, it was lower than the split toe foot, so our design did improve in that case from the split toe to the narrow foot. And for toe off, it's lower than the silhouette foot, which we think is probably because it's more of a rocker motion instead of this spring toe off from our subject's prosthetic foot. And for the inferior moment, ours is the second lowest, but we thought that maybe because our foam didn't have the best traction, that could also be attributed to slipping on the floor.
These are the goals that we set at the beginning of the semester that we hope to accomplish by now. So we performed research and decided on a top design to go forward with. We produced 2 working prototypes and produced professional engineering drawings and FEA in SolidWorks. If we had more time, we would continue with performing ISO testing on this narrow foot with static and dynamic conditions to see how the foot will perform under cyclic and sustained loading, and then redesign and retest as needed in the future.
And again, we would like to thank you all to being here and join us today. And we would like also to thank all the people listed here, Jim Cardin and his student, and Jake and Paul and Claudio he helped us with the sidewalk, and Rai and Olympics International also. And special thanks for Dr. Arico for everything. Thanks.
What rubber spacers you used when they replaced the spring, and did you think of any?
And it was cheap.
Do you think of any of its properties to take a look at?
We bought 2 different types of rubber, and we used the one that was squishier.
Okay.
Very scientific. Yes.
Yeah, we'll start with that.
Are there any other materials that you might consider rather than Delrin?
There are a lot of different plastics that we could use that are would be more lightweight, but the reason we went with Delrin especially was because LIMS already has a manufacturing plant in Bangladesh, so they already have all the tools and materials that could make this foot.
It's also relatively low cost. Like something better would be fiberglass or carbon fiber, but those are very expensive, even though they're lightweight.
How do you plan on getting it down to like a $20 foot that you had mentioned? Do you plan on molding this at some point if this were to go full blown, or is it going to be core machined?
We're not exactly sure. I think that the manufacturing plant in Bangladesh does molding.
LIMS
Dr.
International has just, typically the way they ran previously was each site built their own knees, because knees are what they have right now. But they're starting to change over to, they have a mass production plant. I'm not sure, last year I heard that they were getting going and they weren't quite up to full production yet. But this plant does injection molding of the knees. So ideally that may be the final step if this foot
Because
goes.
injection molding would allow you to put that spring in there if you wanted to.
Oh, really?
also.
Okay. Good to know.
You looked at about 7 or 8 different criteria. Was there one that stood out as being most important in terms of your matching?
Functional, probably, and easy to manufacture. Probably were the highest.
The pad on the bottom has to be replaceable, I assume, because that would wear out.
Right. Yeah.
And so that's a bonding operation using PC?
That's how we did it. We would ideally in the future be able to create some kind of cosmesis that would go over it, but we didn't really have time to get that far.
The foam sole is mainly for the subject testing performed at school, so you wouldn't slip out on the floor.
Right, because Delrin is a slippery material. You
Yeah.
can't have electricity. You couldn't use Delrin itself.
So once we learned we wanted to make our foot out of Delrin, we contacted about 12 vocational schools around Connecticut to see if they could make the foot out of a milling machine. And a lot of schools got back to us about 3D printing the foot, but that wasn't the direction we wanted to head because that would cost a lot of money. We would probably have to pay for the cartridges to go in the 3D printer, and I don't think they have Delrin cartridges anyway. So Windham Tech actually got back to us, Jim got back, and he said that he would be able to do it with the CNC machine, which would be ideal for us. So that worked out really well, and I'm glad he got back to us with it.
Hi guys, I'm Tim. I'm a junior here. I'm from New Jersey. I'm a bio major, so I know some of you guys are interested in biomedical engineering, stuff like that. So basically we're just going to take a quick campus tour. I know you guys need to be out by 1, so I'll show you guys pretty much the most important things. But you guys ready?
Yeah.
All right, let's get going then.
Before you head off, I want to say thank you for helping us with the bioengineering project. I was at the talk. It was absolutely wonderful, so we so much appreciate that partnership. Hopefully we'll work together in the future like this. It was a great experience for us.
Absolutely. It was great for us, too.
Capability. Let's do more things like that. We have lots of projects similar to that.
You know who to call.
Yes.
All
Okay,
right.
so now we know. Good. Thanks, Joyce.
Come on.